Greetings, I am Prashant. Myself, my teammates SUSINDHAR, SENTHAMIZHAN and ANGELIN are here now to present on conceptual designing of an aircraft. So the aircraft we have chosen is Antonov AN225. It is a strategic airlift cargo aircraft that was designed by Antonov Design Bureau in the Ukrainian SSR within the Soviet Union during 1980s. The Antonov AN225 was initially developed as an enlargement of the Antonov AN124 to transport Buran-class orbiters. The only AN225 airplane was completed in 1988. After successfully fulfilling its Soviet military missions, it was mothballed for 8 years. It was then refurbished and reintroduced, and is in commercial operation with Antonov Airlines, carrying oversized payloads. The airlifter holds the absolute world record for an airlifted single item payload of 1,89,980 kg and an airlifted total payload of 2,53,820 kg. It has also transported a payload of 2,47,000 kg on a commercial flight. Now, my colleague ANGELIN will speak on its technical specification.
So now what you are looking is the specification of a chosen aircraft. Exterior height 18.1 meter, wingspan 88.4 meter, length 84 meter, crew 6, maximum thrust 23,430 kgf, empty weight 2,85,000 kg, fuel capacity greater than 3 lakh kg, range 15,000 km, service ceiling 11,000 meter, maximum speed 850 km per hour, normal cruise 800 km per hour, engine 6, engine Ivanchenko Progress D18T turbofan engines.
So now in order to proceed on to designing of an aircraft, we have to first perform initial sizing. Initial sizing is usually the first step in the conceptual design process, but it is also an optimization task. As it is the very first step, it is typically carried out with the lowest number of design variables and design constraints. This reduces accuracy but increases efficiency. The main objective here is to identify requirements that are likely to drive the design, and its first step is to estimate the size of an aircraft through the estimation of its design gross weight at the start of the design mission profile, which is provided by the user. Additionally, some requirements of the regulatory authority is looked upon. So now my colleague SENTHAMIZHAN will proceed.
Okay, now we will be looking into weight estimation of our aircraft. As represented, the equation of initial sizing is W0 equal to W crew plus W pay plus W fuel plus W empty, which can be elaborated into W0 equal to W crew plus W pay divided by 1 minus empty weight fraction plus fuel weight fraction. First we will estimate W crew. Since our aircraft is an cargo flight, we do not have to consider cabin crew. Our aircraft will have 6 crew to it, and we will assume 100 kg for each crew member, giving us a total W crew equal to 600 kg. Now we will do empty weight fraction calculation. You can clearly see for the PPT how we proceed, what formula we used and what value we used, etc., and we get the value empty weight fraction equal to 1.01. Now my colleague SUSINDHAR will take on.
So now we are looking into the mission profile for our aircraft, which can be clearly seen in the slides. 0 to 1 is takeoff, 1 to 2 is climb, 2 to 3 is cruise, and 3, 4, 5 are loiter conditions. 5 to 6 is diversion, and 6 to 7 is landing. This 5 to 6 diversion part is a little different and extra for since our aircraft is cargo flight and is different from the regular conventional passenger aircrafts. So now we are looking onto the formula for estimation of mission fuel fraction, which is W fuel equal to W mission fuel plus W reserve fuel. W mission fuel depends on type of mission, the aircraft aerodynamics and engine SFC, which is specific fuel consumption. whereas W reserve is required because sometimes the aircraft can miss the landing approach, or diversion and hole can be amplified, or navigation errors. And there are some assumptions for our calculation that we consider. You can be seen from the slides. And what is displayed here is the estimation of mission segment weights, and the total fuel weight fraction formula is displayed over here from the slides, from which the warm-up W1 bar W0, the takeoff W2 bar W1, and landing weight fraction W7 bar W6 are estimated and assigned from historical trends. The values are shown in the below table. The warm-up and takeoff value is 0.970, the climb is 0.995, and the landing is 0.995. So now what else values do we need? We need W6 by W5, W5 by W4, and W3 by W2, in which W6 by W5 and W5 by W4 are loiter conditions. And since loiter may vary from mission to mission, and assuming that such huge aircraft with high importance will not be denied for landing or be given with the loiter, we assume that loiter values to be 1, which is seen in the slides, which can be seen from the slides. W6 by W5 equal to 1 and W5 by W4 equal to 1. Now all we need is W3 by W2 value, and the table here shows the some required parameters. The H cruise is altitude for our aircraft, which is 11,000 meters, and M cruise is Mach number in cruise condition, which is 0.65, and R cruise is range, which is 15,400 kilometers. And now we are entering the estimation of fuel weight fraction in cruise segment for W3 by W2. We are using a bracket range equation, which can be seen from the slides, and for which we need L bar D cruise. To calculate L bar D cruise, we have to first calculate L bar D max from the historical graphs and value trends. We estimate S wet by S ref equal to 8, and aspect ratio of our aircraft's wing will be 8.6. By having this value, we calculate wetted A wing, which is 1.075, and from which we got the value L bar D max equal to 17.2. And in this slide we can see the other values that are required for the calculation. Via our SFC cruise, we are converting the value to per seconds, which is 15.19 into 10 to the power minus 5 per second, and calculation of V cruise and L bar D cruise also can be seen. And by using all the calculated and assumed values by using the values in the bracket equations, we get the value W3 by W2, which is 0.440, and assigning that value to W7 by W0, we get W7 by W0 equal to 0.4182. And using this value, we are calculating fuel weight fraction. To the calculation of fuel weight fraction, we need RFF, which is nothing but reserve fuel fraction. We have assumed reserve fuel to be 10%, and by the calculation we get a fuel weight fraction, fuel weight fraction's value to be 0.6399. Here we can see descent gross weight estimation from the formula. By using all the values, W crew we calculated 600 kgs, and we know W payload, and just before we calculated a fuel weight fraction. By using all this value, we get W naught to be 2,54,418.35 kilograms. From here my colleague Angel will continue.
So this will be our aircraft's wing sizing. We have used this lift formula and below mentioned parameters to estimate surface area of our wing, which is 800 meters square. And using modified aspect ratio formula, we calculated wingspan, which is to be 84.8.85 meter.
As far as wing plane form concerned, the wing configuration we have chosen is high mounted dihedral wings. The high mounted wing is above the aircraft's center of gravity, which confer extra dihedral force due to the pendulum effect maneuvered. The advantages of high wing can be seen from the slide.
Such designs can also have excessive dihedral effect and so be excessively stable in the spiral mode. So anhedral angle on the wing is added to cancel out some of the dihedral effect so that the aircraft can be more easily handled. The twin tail was essential to enable the plane to carry large, heavy external loads that would disturb the airflow around a conventional tail.
For the landing gears of this heavy aircraft, we have chosen multi-bogie configuration and has nose gear designed to kneel so that cargo can be easily loaded and unloaded. So what now you're looking into is the engine spec of our aircraft.
That will be all for our presentation. Thank you.